Okay, in this one, I want to explain how what we did in the last video for solving the heat equation under a very specific initial condition, how we can use those as sort of building blocks to solving the heat equation for general initial conditions. So just as a quick reminder, the problem that we're really interested in solving is this one here. We have the partial differential equation, alpha u sub xx is equal to u sub t. That's called the heat equation. It governs the dynamics of heat distributed in a one-dimensional bar. And by the way, there's versions of the heat equations in higher dimensions. So if you're interested in the distribution of heat in funny shaped metal plates or in funny shaped metal solid objects, there are higher dimensional versions of the heat equation. You replace this u sub xx here by something called a Laplacian, okay, of u. Again, it's PDE stuff. It's heavy. Here are the boundary conditions that we are going to work with. The two ends of the bar are going to be kept at 0 degrees, and then we have an initial condition that at time t equal to 0, the initial distribution of heat in the bar is going to be given by this function f of x. All right? Now, we solved a certain heat equation in the last video. We solved it under the same heat equation, the same boundary conditions on the bar, but with a very highly specified initial condition, namely that the initial distribution of heat in the bar is given by sine n pi over L times x. Okay? But what I want to say is that with a little bit of work, we can use these solutions here to build a solution for the general f of x problem. How? What we're going to do is form something called the sine series of f of x. So right now, our function f of x, it's the initial distribution of heat in this bar of length L, okay? So what I want to say, the way I want you to think about it is that we have this function f right now. F defines the heat distribution at time t equals 0 for x between 0 and L, for x between x equal to 0 and x equal to L. It's a little bit wordy, but whatever. Okay, so we've got f defined from 0 to L. I want to bring to bear the power of Fourier series to express f in terms of these signs, okay? Sine n pi over L times x, okay? We know that sine n pi over L times x are building blocks that are used in the Fourier series for 2L periodic functions. But there are other building blocks. There are the cosine n pi over L's, for example, okay? How can I avoid the cosine n pi over L times x's and the constant term that we know appear in the Fourier series, the full-fledged Fourier series, okay? To avoid the cosine terms, I'll call them, in the Fourier series, the trick is that we are going to extend f to a function from negative L to L. Right now it's only defined from 0 to L, the length of the bar. We're going to define it from negative L to L, okay? Extend f to the interval from negative L to L. And crucially, we're going to make it an odd function. Odd, O-D-E. No, that's not how you spell odd. That's how you spell ode. Odd is O-D-D. Oppositional defiant disorder. But that's not what I'm talking about. Odd. An odd function. We want to extend f to the interval from negative L to L to make it, and this is the crucial part, an odd function. So here's what I'm talking about here. If we have f defined, let's say, in the following way, maybe it looks like this. Okay, this is from 0 to L. This is what it looks like. Then what I want to do is I want to extend this function from negative L to L. So here's how I'm going to do it. Take this guy, duplicate it, move it over here. I'm going to keep it from the same thing from 0 to L, but I'm going to define it further from negative L to 0. Maybe negative L is over here. And I'm going to define it in such a way that it's an odd function from negative L to L. So what that means, I have to take this picture and rotate it 180 degrees. If I do that rotation and I carry this green curve with me, I'm going to get something, and you're going to have to deal with my bad drawing skills. Something that looks something like this. Oh my gosh, I'm not happy. Like that. Okay, that looks pretty good. Do you see how now this thing has that 180 degree symmetry about the origin? It has that the oddness property that if you plug in negative x, you get negative of f of x. Okay? So this is an odd function. This is what we call the odd extension of f to the interval from negative L to L. Once you have this, now extend periodically. Now extend this function to a 2L periodic function. So we're going to copy this picture between negative L and L and just copy it every 2L units, both in the positive direction and in the negative direction. I won't try to draw that because I'm not good at drawing. Okay? You're going to use your imagination. All right. Then, crucial insight, the Fourier series will only have sine terms. Okay? This is amazing. Why? Because if we write down a sub n is something like 1 over L times the integral from negative L to L of f of x times cosine n pi over L times x dx. Okay? But crucially, this function now from negative L to L is odd. And this part here, that well known to be even. The product of an odd times an even is odd. And when you integrate an odd function over a symmetric interval, you get 0. Therefore, this is equal to 0 for all n. Okay? So all the coefficients a sub n are going to be 0 by the standard formulas Fourier series. And all we're going to have, the only possible things that we're going to have are sine terms, the b sub n's. Right? Those might be non-zero. Okay? Now, once you have the b sub n's, okay, what this means is that we can express, we can write f of x as the sum from n equals 1 to infinity of b sub n times sine n pi x over L. N pi over L times x. Yeah? Where, of course, we know what b sub n is. It's given by 1 over L times the integral from negative L to L of f of x sine n pi over L times x dx. Okay? Amazing. Okay? Because what we've done now is expressed, going back to our differential equation now, we've expressed our initial condition f of x as a sum, an infinite sum, sure, but a sum of these sine n pi over L times x's. Yes? That's what we've done here. And once we have that solution, once we have that that expression for f of x in terms of as an infinite sum of those signs, we just all we need to do to get a solution to our differential equation is to mash together to mash together in the right way the correct u sub n's. Okay, so we can use this. Let me write all this down. So a solution to the heat equation with, oh, that's not how you spell with initial conditions given by u of x comma 0 being f of x is the following. We're going to have u of x comma t. Maybe I'll do this in red because I feel like it. U of x comma t is equal to the sum from n equals 1 to infinity of b sub n times, well, u sub n of x comma t to start with. But that's the sum. It's hard for me to write with these Apple pencils. Sum from n equals 1 to infinity of b sub n times sine of n pi over L times x times the exponential of negative n squared pi squared over L squared times alpha times t. That's it. We've now solved the heat equation. It's an infinite sum, sure. And you might be saying to yourself, my God, how am I ever going to actually use an infinite sum? The idea, of course, is that you're going to take advantage of the rate of, you're going to take advantage of the fact that this thing converges by using a computer to calculate the first 100 terms of this, or maybe the first 50 or 10 or 2. Okay, it's some number of terms of this infinite sum here as an approximation to the solution to the heat equation. Okay, and please note, okay, how sensible this this solution is. Okay, it's sort of saying here, because we have these decaying exponentials, note the negative sign, and note the fact that this number here is going to be positive. Because we have those decaying exponentials, we're going to have, no matter what the initial distribution of heat will be, we'll have that with time, the distribution of heat will normalize to 0. All of the heat, in other words, is going to escape out the ends of and into the ice bath, which is maintained at 0 degrees. Okay? Which I think is what your common sense would suggest. All right? Cool. Very cool. So we learned a couple of things here. We learned that we can use the solutions that we found in the last video as building blocks. Okay? And once we have those building blocks, we can construct the solution to the heat equation for general. Oh, right. And how do we take advantage of that? Well, we express f. Oh, shoot. We express f as an infinite sum of sines. Exactly, these are exactly the building blocks that we have here. And it's going to be a grand superposition where the weights of that superposition are the b sub n's. These weights exactly appear in the solution to the heat equation. Okay, cool. All of this is taking hardcore advantage of the linearity of the heat equation. Okay, that's enough. So long.